So good afternoon everyone. So welcome to the session. So let's wait for some time before other guys come. So before that we can start with the pre-activity. Okay. Yeah. So I am Hariccharan. So I am a coordinator in Hariccharan, and this is Srikiran.
No.
So he is also coordinator in Hariccharan. So we will be presenting today's session. So yeah. So let us start with the pre-activity before going into the session. So you guys know that this session is something related to colors. I hope you guys know. So why is it important to study colors beyond interest? What is important in colors? What are the real life applications of color theory? What do you think? Holy, no.
Interesting.
Holy, maybe. Any real life example? Yeah. Sharing informations. Okay. Nice. Cure color blindness. Nice. Okay, so colors, as they said, apart from that, it is used in designing screens, and we also have photography, which has a lot to do with colors. So let us have a pre-activity related to photography. So this is some of the most important photographs which made milestone in the history of photographies. So can you guys tell what are these photographs? So what is this photograph? What may be the photograph? You guys can guess. You need not tell what is in the photograph. You can tell the context behind the photograph, what it may be. Yeah, yes, please. Great Wall of China. Okay.
Interesting. Sort of. What? Yes.
Yeah, this is the first photograph that was ever taken. So this was taken in 1826 to around 27. So this is the window at a city named Lagras. So the window view of a city named Lagras. So this photo has several hours of exposure. So maybe even days. So yeah, so this happened in 1826. So many years before, much before great revolt of 1857 in India. So yeah. And then we have our next photograph. What may be this photograph? What does it look like? Any guesses?
Huh?
First photograph of the moon. Okay. Interesting. Eclipse.
Okay. Looks like on
Okay. Okay. Sorry.
Who's? Dewdrop.
Dewdrop. Okay. Nice. Okay. Let us reveal. So as she said, it is the first photograph of the moon. So this was taken in 1840 by John William. So this photograph has about 20 minutes exposure. So this was taken so many years before. That is why it looks like a microscopic image. Okay, next, what may be this image? Any guesses?
Crystal.
Crystal,
like
no.
Crystal.
Okay, so let's see. So this is actually a ribbon, a tartan ribbon. So this is the first color photograph that was taken. So this photograph was taken by Thomas Sutton in 1861. So Thomas Sutton was actually working with James Clerk Maxwell. You guys will know Maxwell, the one who compiled the equations of electrodynamics. So he was the one who proposed that we can mix red, green and blue to obtain color images. So if you had seen the previous Guide to Galaxy session, it was based on special relativity, and Maxwell's work directly led to special relativity by Einstein. So Maxwell played a major role in color theory and special relativity. Okay, what may be this image?
Is it still first video or something?
Yeah,
Yes.
I want to see it as well.
nice. So it's the first video. So this is the Roundhay garden scene, the first video that was taken in 1888. So it was about 2.11 seconds long. So yeah. Now these images, you may have seen some images somewhere in your textbooks perhaps. So what is this image? You guys can guess. With the pattern of the images we have seen so long, you can guess what this image may be. First color portrait.
But-
Photo. Okay.
Okay. Of a person.
Of a person. Okay. Okay. Any other guesses? Okay, let me reveal. So this is the first video, color video. This is the first color video. So this was taken by Edward Raymond Turner. So he was a scientist come entrepreneur. So he designed a color video camera, and these are his 3 daughters. He tested with his 3 daughters who are playing with sunflowers. Yeah, so this was taken in 1901. And this image, do you guys know this image? Have you seen somewhere? This may be there in your... Yeah.
Yes.
So this is the migrant women. So this photo is used to represent the Great Depression that happened after the First World War. So after the First World War, every country had a very bad economy, and so this shows a woman starving with her 3 children. The name of the woman is Florence Owens Thompson. So she did not have enough food during the Great Depression, and the photographer is Dorothea Lange. She took her photo and published it, and till now this photo is used to represent the condition of people during the Great Depression. Yeah, and this photograph has its own story. So do you guys know this photograph? This last one. What does it look like? What can you see in the photograph? Sorry.
Is it a forest fire?
Forest fire.
Yes, I guess.
Okay. Okay. Nearby. You are nearby. First
No.
landscape.
So his answer was the forest fire answer was closer. Something worse than a forest fire.
Volcanic eruption. Yeah.
I don't know who's.
So this was a volcanic eruption in 1890 of Mount Helens. 1980 of Mount Helens. 1980 of Mount Helens in the Washington state of United States. And the person who took this photo was Robert Landsberg. He, yeah, this is the exception, cameraman. So that's the story. He was so close to the eruption, and he did not predict that the eruption would be this powerful. After taking the image, he did not run, or he did not try to save his life. So instead he took the photo and kept it in his bag, hugged his bag and laid down, so that even if he dies, his photo will survive. So he had such love for his creations. So it is an important photograph. So the person was Robert Landsberg. And these photos will be in some of our backgrounds across our slides. And let us go into the session. So welcome to the session, and this is Horizon's second Guide to Galaxy session. Physics of colors. Yeah.
So before we study anything about colors, we can first look at the history behind what people thought of colors. So before Newton's experiment, people thought that white light was the purest form of light, and that whenever you saw color, the object that interacted with the light modified the white light to create the color. So basically what they thought was, if you had a blue tinted glass, if white light passed through it, then it modified the white light to give you blue light. They didn't think that white light was composed of the different colors. So Newton had so people also had knew about the dispersive nature of prisms before Newton, but they didn't call it dispersion. They thought that the prism was modifying the white light and generating the colors. So there was a fair near. It's not loud. Okay, fine. Is this turned off? There was a fair near Newton's college where they were selling these prisms, and Newton bought one prism for fun, and he conducted the experiment. Sorry. He sent sunlight through this, and well, you all know what happened. He got dispersion like this. But he wanted to see what would happen if he sent only one of the colors through the prism again. According to what people thought at that time, the prism should do something else to the light that's sent and generate other colors. But obviously that's not what happened. So he wanted to test this out, but then the fair got over by that time, and he had to wait one more year to buy another prism and complete his experiment, which confirmed that. So let's say this is red light. He sent red light through this prism, and he only saw red light again. So the prism was not doing something to the light that was entering it and generating more colors. He concluded that the prism was instead separating the white light into its component colors. So this was a good thing and a bad thing. First, it clarified the misconception that white light was the purest form of light and every other color is a modification of white light. But then, following Newton's discovery, all further analysis of color was only done through physics. And for about 200 years or something like that, people didn't think about involving biology into the perception of colors. In our session today, we'll be playing with both physics and biology to explain the perception of colors.
So you guys might have known about this experiment before, and okay, fine, no problem. And white light is composed of 7 colors with GR. Why 7? So here the colors vary gradually. Why is 7?
Is that the minimum number of colors we can distinguish between something?
No. So initially when Newton found, he distinguished 5 colors, and he also saw that the colors vary gradually, and Newton, he himself was a holy man, so 7 is a holy number, so he just added 2 colors to make it to 7. So that is why there are 7 colors with GR. Okay, so yeah, let's.
What were the colors that he added?
Violet and indigo, I guess. Yeah. So let us look about violet and indigo in later slides, what's special about them. And yeah, so from as Srikiran said, till 19th century people thought color was some inherent property of light. They did not think that it was our eyes that helped to see us colors. So it was still Thomas Young and Helmholtz in 1802 who proposed the tricolor theory, and they explained that all colors are produced by mixing 3 colors. Yeah. What helps us see? Eyes. Yeah. Eyes helps us see, and this is the basic structure of the eye. So yeah, so this is how eyes enter. The light enters the eye. So this is cornea, and this is the iris, this is pupil, this is the lens, and lens focuses the image on the fovea, the retina, especially in the fovea, where there is a higher concentration of optical receptors, and this is the optic nerve which enters the eye. When the optic nerve enters the eye, there are no receptors here, forming a blind spot, and in the fovea we have a larger concentration of optical receptors, so we have a clear vision when the image is focused at the fovea. So let us look at the types of optical receptors. So human beings can see colors from about 380 nanometers to 750 nanometers. So yeah, okay. And there are 2 types of optical receptors. One is rods, the other is cones. Rods helps us to detect light, giving us a black and white image, and cones is the one which gives us colors. There are three types of cones. One is the L cone, M cone and S cone. L cone corresponds to the longer wavelength, M corresponds to the medium wavelength, S corresponds to the short wavelength. So L cones have their maximum excitation at 570 nanometers. M cones have the maximum excitation at 540 and S cones at 450 nanometers. And all cones are made up of a special pigment called photopsin which helps them to get excited. There are about 120 million rods and only 6 million cones. So this is about 5% of total number of cones nearly, and all those 6 million cones are near the fovea, because that is the region where the image is seen clearly. Rest of the retina is filled with rods. Yeah, so this shows the intensity graph of different types of cones. For the S cone, say the blue cone, so for the S cone this is the responsivity curve, and for a green cone this is the responsivity curve, and as we can see it is not equal. Different cones have different responsivity and different extent of responsivity as well. For a given blue light, blue cone has a lesser excitation compared with green light. So but this is not important when we are analyzing the formation of colors. All that is important is a normalized responsivity. That is what we are going to do, is that we are going to divide every responsivity curve by the maximum value. For the blue cone we are going to divide by this value, for green cone by this value, and for the red cone by this value. We get the normalized responsivity curve. So this is the normalized responsivity curve, and as you can see the S cone attains the maximum near blue region, so it is also called the blue cone. But the M cone and L cone are called green cone and red cone, but they don't correspond to green and red. Let us see why. So now what I am going to do to analyze colors scientifically, what I am going to do is that I am going to take these S, M and L values and I am going to plot it in a three-dimensional space. So in my space, this is L, that is excitation of L cone. This is M and this represents S. Now I am going to plot the excitation of each and every single color and looks how they are. So this is how the colors are distributed in the LMS space. The space created by these three axes is called as LMS space, and these are the spectral colors. So as you can see, 380 nanometers starts here, and as I am increasing around 450 nanometers, this is the maximum for S cone, and as I am increasing at 540 nanometers, I attain the maximum for M cone, around 570 nanometer maximum for L cone, and again to 0. So if you can see in this graph, if you see this graph, this is a plot which I made in Python. Oh, not here. Spectral color. Yeah. So if you can see the graph is not symmetric. Why is the graph not symmetric? Why do you think the graph is not symmetric? Why is it some random shape?
Some colors are more important for us to identify to avoid poison, something like that.
We will come to that later. Why did we develop colors? We can come to that later. Yeah. So my question is that why is there is a sharp lobe for blue region, but we don't see such a lobe for green and red region? So the graph should have been like this, but why is it like this?
Because there's like too much overlap between green.
Yeah. So if you see here, there is a lot of overlap between M and L cones. So because of that, whenever the M cone is at maximum, the L cone is always excited, and whenever the L cone is maximum, M cone is always excited. So these types of excitations are not possible. Pure M cone excitation, pure L cone excitations. And another important question, look at this graph. Where is violet in this graph? Where is the color violet? Here. No, this is red. I can go to the other graph and show. So yeah, so this is the colors that are there. I am going along the curve. So did you guys see violet? No. Yeah, there is no violet. Violet is not a spectral color. So but still Newton defines violet as a spectral color. That is because during Newtonian times the definition of violet was different. During Newtonian times violet was this color, dark blue, and during his time cyan was blue, and now the definition of colors have changed. And but still if we look at a rainbow we will be able to see violet. We know rainbow is sunlight getting refracted. And why is violet present in a rainbow? Any guesses? If violet is not a spectral color, why do we have it in a rainbow? No, we can see rainbow and we will be able to see violet.
We have multiple rainbows and the violet and blue of one and the red of the other overlap with each other.
Yeah. So there are multiple rainbows, and the blue of the primary rainbow would interfere with the red of the supernumerary rainbows, giving violet color. So violet can be obtained by mixing the spectral colors. Spectral colors correspond to individual wavelengths, but other colors are a mix of wavelengths. So violet is a mix of wavelengths, cyan, magenta, they are all mixes of wavelengths. So yeah. So by this what we understand is that the colors, the LMS values are not functions of wavelength. They are actually the functions of the intensity spectrum of wavelength. Intensity spectrum is easy. So it is just the intensity of light expressed as a function of lambda. You guys can see this, right? This graph, or else I can draw it here. So this is the intensity function expressed as a function of lambda. So for example, how would an intensity function look for a monochromatic light? Like this? No, it would be like this. That is because the total intensity is the integral of the intensity spectrum. If the total intensity is constant, then this function must go to infinity for a very small interval of lambda. So this is how monochromatic intensity spectrums look like. If I take for white, white would be like this, almost like this. There will be something like this. This is how white would look like. And for pink, pink would be like this. So this is how the intensity spectrum would look like. Now what we can do, we can give different intensity spectrums into our LMS functions and see the colors. I want to change the graph. When changing graph takes time. Okay. Where is the function? Yeah. Okay. What you are seeing here is that I have given the pure intensity spectrum for 450 nanometers, and this is the color I obtained, and these are the RGB values. You can see blue is maximum, and we know that at 450 nanometers blue is maximum. Now let us do the same for 540 nanometers and 570 nanometers. So this is for 540 nanometers. It is in pure green, it is some yellowish mixed green. Now let us do for 570 nanometers. Yeah. So this is how 570 nanometers looks like. So 570 nanometer is the value where the L cone reaches the peak, and it is not red, it is yellow. So to obtain red, we have to go to 620 nanometers. And we have red. So at 620 nanometers, this is my responsitivity graph. This is M and this is L. At 570, my M value would also be high, but at 620 or 630, the L value would be medium, would not be high, but the M value would be negligible. So I see red beyond 600 nanometers only. That is why we don't always call the LMS cones as the red, green, blue cones. We must not call them like that. Yeah. And now let us look at other possible colors. So what you see here is a plot of all possible colors in the LMS region. So the image which you see here contains all possible colors that we can see, obtained by mixing all possible spectral colors. So yeah, so this is the graph. Yeah, so what you see is the 3 dimensions, all possible colors in the LMS curve. So as you can see, it is not covering the entire LMS space, because as I said, the green and red have a higher amount of overlap between each other. So we don't have colors in this region and this region. So this leads to a fundamental problem. What is the problem is that everything the eyes does is to send the LMS input to the brain. Now brain will allocate colors based on the LMS value. The brain can allocate colors for all possible LMS value inside this cube, but the eyes are designed such that we can take inputs only in this region. So what happens if I provide a stimulated input in this region? What would I see? I am controlling my cones such that I am providing an input as this region. What would I see? Black and white. Okay. Any other guesses? What would I see if I am giving an input that is outside the gamut? Gamut is the collection of all colors. I am providing an input outside the gamut. What would I see?
A different color.
A different color. A color which we have never seen before. The color which we can imagine but which we don't see in our day-to-day life. So we will come to that. Now I want you guys to do an exercise. I want you guys to focus at this red point. Just focus at this red point for some time. Don't change your focus. 3, 5, 6, 7. Okay, keep focusing at the red point. Don't change your focus. And what do you see? What do you guys see? What did you guys see? You can say, what did you see? Shadows. Okay. The US flag. You guys should have seen the US flag, because what I showed here was the negation of the US flag. So what happens here is what we call the after image. And why after image occurs? So the tricolor theory that was proposed was not able to explain these after images. So that is when we came up with the opponent process theory. The opponent process theory was proposed by Hariccharan in the late 18th century. According to this theory, we perceive colors as 3 antagonistic pairs. We see them as black or white, blue or yellow, green or red. So every color will have 3 components: black to white, blue to yellow, green to red. So when one color is high, the other color is inhibited. So I can explain this intuitively why this happens. So let us consider we have 3 farms and you are getting apples from these 3 farms. First farms are providing an apple which is slightly yellowish in color, a different variety of apple, and the other 2 farms are providing the same variety of apple which looks similar, but you want to distinguish them. So what you are doing, you are going to put those 2 apples in bags of opposite colors, and the apples from the first farm can be in any other bag. So the same happens here. As I said, the L and M values are overlapping with each other. So to distinguish them, our brain processes red opposite to green when other channels are constant. When other channels are constant, red is opposite to green. So because of that, and similarly blue is opposite to yellow, and naturally black is opposite to white. We have this intuition, black is opposite to white, blue is opposite to yellow, red is opposite to green. So because of this combination, all colors in the visible gamut will have an opposite color in the visible gamut, and that is what you saw here. When I show this image for some time, what happened is that all the cones that gives yellow color and cyan and black in the respective region of your eye got fatigued or tired because they were seeing the same image for about 30 seconds. So when I showed white is made up of all possible colors. So what happens, the color corresponding to yellow, the cones corresponding to yellow, they did not have a higher level of excitation because they were tired. The colors corresponding to blue, they had a higher excitation. Now what blue is doing, blue is suppressing yellow according to the opponent process theory, and you see the negation of the image, which would be the American flag. This is how the after images work. And then now to understand more about colors, we are going to define some parameters for these colors. So after this, what we are going to see is some mathematical analysis of how to understand perception of colors. So now what is luminance? Luminance is nothing but it relates to the intensity of color. If a color has a higher brightness, it has a higher luminance. That if the color has a higher intensity, it has a higher luminance. If I am reducing the number of photons in the given light, the luminance would reduce. And then what is chroma? Chroma is the property of color irrespective of the luminance. That is, green would have a different chroma from blue, from red, from yellow. All have different chromas. But grey, black, white, they all have the same chroma. They are just a change in luminance. They are not variation in chroma. So this is the LMS graph, and what you are seeing is a line. I have taken one point in the visible spectrum, visible gamut, and this is the origin. I have connected this point and the origin. What is the special property of this line is that this line has constant chroma. As I am moving from origin to this point, only the luminance is changing, only the brightness is changing. Why is this important? That is because now we are going to a different space from the LMS space. Why should we go to a different space? Because this space, LMS space, does not explain opponent process at all. We can't intuitively understand opponent process from LMS space, and we need a better understanding. We need to understand luminance and chroma in a better way. So we need a better space, and this new space must help us to make it must help us in our practical applications. So that is why we come with the CIE XYZ space. So this is nothing but a linear transformation of the LMS space. That is nothing but we would multiply this matrix with the LMS values, and we would get the XYZ values. How did they get this matrix? So scientists in 1930, they gathered a group of people, they gave them a lot of colors, and they asked them to distinguish the colors. ask them to arrange the colors which perceived to be related colors, they spaced them nearby, and the colors which were not very much different were spaced apart. Based on the perception of those people, they designed the CIE XYZ space. So this is a CIE XYZ space, and if you see in this thing, this is red. This is the point where red is there. This is green is here. So red or green in the opposite direction. And I have yellow in the bottom. I have blue in the top. So they are opposite to each other. If I express all the colors in this space, white would be somewhere here above green, and black is here. White and black are opposite to each other. So this graph explains the opponent process theory. And now what I am going to do is that I am going to take the CIE XYZ space and I am going to remove luminance from the equation. How am I going to do? I am going to project the entire space about this plane, x plus y plus z equal to 1. When I do that, out of 3 coordinates, 1 coordinate is removed, and that coordinate comes out to be luminance. So when I do that, what I get is this, the chromaticity diagram. So this is nothing but the cross section of the LMS gamut with the plane. After taking the cross section, I am filling each point with the corresponding chroma of maximum luminance. So if you see here also we will be able to understand the opponent process theory. The x-axis corresponds to green-red separation. The x value is least here, it is maximum for red. So green and red are opposite to each other. And the luminous efficiency corresponds to the relative brightness of colors. As I said in the first slides, that green has a higher green cones have a higher efficiency than red than blue. So here green is at the top, red is here, blue is at the bottom. And 1 minus x minus z, it comes from the plane's equation, x plus y plus z equals 1. So this represents yellow to blue. When I am coming by 1 minus x minus y axis, like this somewhere, x equal to y line, it comes from yellow to blue. They are the opposite places. So all possible colors that humans see, irrespective of luminance, is in this graph. So this graph is what the screen makers, they try to make their screen such that all possible colors are present in their screen. So this is what they use to make screens.
So what are the axes in this image? So like I think y-axis is like the
yeah, so one second. So if you see here, this is my CIE XYZ gamut space, and what I am going to do, I am going to compress it about x plus y plus z equal to 1 axis, and this is how it will look like. Now what I am going to do, only 2 parameters are there in this plane. I am going to remove the z parameter. I am going to plot the x and y values. Oh, not this. One sec. So if when you plot it, we get this thing. We will get this. So we have the x-axis and y-axis. The x and y are obtained with this formula. This is a normalization formula. If I do this, I will project it on the x plus y plus z equal to 1 plane. So yeah, now this is the grayscale diagram of the chromaticity diagram. This is just representing the relative luminance. You see, white has the highest relative luminance compared with green. Green is higher than both red and blue. This equation gives the weightage. Green has 0.5, red has 0.2, lesser than 0.5, and blue is least. As I said, that all the colors that are outside the gamut, inside the LMS cube, correspond to the colors that we can imagine, but the colors which we don't see in our day-to-day lives. because our cones cannot be excited that way. So what people did is that scientists at the University of California in this year, April 2025, they designed a setup. What is this experiment doing is that it is first going to analyze your retina. By analyzing your retina, it will find the position of your cones, L cones, M cones and S cones. And this device will send only the green lasers only to the M cones, not to the L cones, not to the S cones. So M cones will have the maximum excitation, L cones will have zero excitation in this experiment, and S cones will have zero excitation. So the people who did this experiment, what they saw is a super saturated blue-green, a color which they never see in day-to-day life. They named this color as Olo. And this is not the color, this is the color in the visible gamut which is closest to Olo. So this is more saturated version of this is Olo. So yeah, and I have a thought question for you guys. If brain can process such colors, why don't we see these colors in dreams? Does anybody have a memory of seeing an unimaginable color in your dream or something? Any weird dream anybody had?
I think dreams are made from everyday experience. So in everyday life we don't see.
So dreams are made with memories. So without memory we don't dream them. So yeah, though these colors can be imagined or processed by the brain, we don't see them in dreams. Yeah, now let us have a look at various sources of colors, sources of lights. Yeah.
Hello. Hello. You can hear me, right? Yeah, fine. So we'll just quickly go over the different sources of light as well as the spectral distribution. So sunlight, you can see over here, it has, at least in the visible region, the spectrum is very uniform. So you get almost all the colors, almost the same intensity. The yellow thing is just sunlight without atmospheric absorption, and in black they've plotted the ideal spectral distribution of a 5000 Kelvin black body. That's it. And in the evenings the sunlight's actually sort of yellowish, because the blue is in the afternoon the sun just comes directly to us. In the afternoon the sun falls directly overhead onto us, but in the evenings it's like somewhere along here. So let's just say this is the atmosphere, and if it's traveling at an oblique angle, it's going to cover a larger distance through the atmosphere, because of which the blue color wavelengths will be scattered more in the atmosphere. So that gives us this like reddish, yellowish light in the evenings. And one more thing is, if you have sat under the shade of a tree in the afternoon, you may have noticed that it looks kind of blue, the shadow looks kind of blue. The reason for that is, if you're in shade, then the direct sunlight's not coming to you, but the light that's coming to you is from the scattered light, and the light that's scattered most is blue light. So that's why shadows look bluish. And then we have incandescent lights. These are also like black bodies, but in this case, since the temperature of the body is very low, and is this even visible at this height? Leave. Yeah. So according to Wien's displacement law, you have this T lambda equal to B. Lambda is the wavelength at which you get your peak intensity, And in normal incandescent bulbs, you have like the temperature is usually equal to like 1500 or 2000 degrees Celsius. That's very less compared to the sun's. And if the temperature is less, and this is a constant, so if the temperature is less, the wavelength has to be the max, the wavelength at which you get max intensity has to be more, so that you get the same constant again. And the problem with incandescent bulbs is they end up heating your room more than lighting it up, which may be preferable during winters, but definitely not in Chennai in summers. If you're talking about black bodies, this plot that you see, this is a plot of the color of the black body with as the temperature changes. So around 1000 degrees Celsius, it looks kind of reddish. Then as it gets hotter, it becomes orangish, then yellow, and finally becomes blue. So the explanation is again can be through Wien's displacement law itself. So as the temperature increases, the wavelength at which you get maximum intensity must decrease. If the wavelength is decreasing, then it's going from like red to blue, and at infinity, basically you'll just have a very at infinity it looks blue because let's say this is visible region, then your plot will look kind of like this. So wait, more uniform than that actually. So it's actually kind of uniform, but there's still a little more blue than the other wavelengths, which is why it looks bluish at infinity. And now about fluorescent bulbs. So fluorescent bulbs are like these kind of bulbs that you might have seen. There's like some kind of spiralish kind of thing. Before we talk about that, we'll talk about fluorescence. So all the materials that you see in this image are illuminated by UV light. Yes. It's not audible. Okay, fine. Okay. Yeah. So all the materials in this image, now is it audible? Yes. All the materials in this image are illuminated by UV light. And what happens here is, so you'll have a ground state at which the electron is there normally, and some higher energy level states as well as other states somewhere else. So when UV light hits the electron, it's like a very high energy photon, because like you have h nu, and if the frequency is more, then it's higher energy basically. That's it. So the electron jumps to this state, and then it comes down to this state without emitting another photon. So the energy that is the energy difference between these two states is instead spent in increasing the vibrations in the atoms around the this atom itself. So that's basically like increasing the temperature of the object. After this, once the electron comes here, then it emits visible light. So that's the process for fluorescence. In fluorescent bulbs, one more thing. Since you have so many atoms close to each other, they end up forming continuous bands like this rather than discrete energy levels. So in normal, if you had discrete energy levels, then you need a photon of the exact energy difference between these two levels to excite an electron from here to here. But if you have continuous bands, you just need a photon that has energy difference equivalent to some energy over here and some energy in this band. And that's enough to excite an electron from this band to this band. So the consequence is that you have a broader range of photons or wavelengths that can, like, you have a broader range of photons that can be emitted, as a result of which, instead of having a spike, you will have like something like this, just a little bit broader. And finally, in fluorescent bulbs, so first they use mercury vapors to emit. So mercury vapors will emit ultraviolet light, which will then excite the fluorescent materials in the bulb, which then give out visible light in this process over here. But you can see over here there are many peaks in the spectra. These peaks that you see here are due to mercury spectrum actually, and all the fluorescent materials are doing is creating these other bumps at other places. So the fluorescent materials are there to sort of give a little bit of every other color that mercury doesn't give. But still, you can see that yellow is not as, the intensity of yellow light is not as high as the intensity of green or the other colors. Because of this, if you had some yellow object, like that fellow's shirt there, then under fluorescent bulbs, it would appear very dull. Yeah, I mean, this is the spectrum if you to compare the two. So these peaks are almost like coinciding, and this is the ultraviolet region which is used to excite the fluorescent materials. And now that we have talked about bands, we can also talk about why gold is yellow in color. So in gold you have the 5D band. I'll just use the same diagram itself. So let's say this is the 5D band and this is the 6S band. So in this case, the energy difference between these two bands corresponds to blue light. And if you shine, let's say, white light on this, which is composed of like a uniform amount of all the different wavelengths, then because of this energy difference between the bands, it will absorb the blue light. And you might ask where the energy that is absorbed is going. Again, it's going to be spent in the vibrations itself. So we'll just increase the temperature a little bit, and at some point you'll get a like equilibrium between the temperature increase caused due to the light hitting it and the like energy loss due to like radiation, thermal radiation. And in silver and aluminium, this energy difference corresponds to light in the UV region. So actually, if that absorbs UV, then like the other light in the blue is like this. So it's not going to absorb any blue light, it'll just reflect all the other light equally. So this is actually just a primer on something else that I wanted to discuss. So we have talked about the different kinds of illumination that lights can, oh wait, there's LED. So LED bulbs are similar to fluorescent bulbs, except here, instead of using mercury to excite your fluorescent materials, the LED itself, which has again broad bands. So if an electron is excited from the conduction band to the valence band to the conduction band, when it comes back to the valence band, it emits a photon. And here also you have a broad range of wavelengths which can be emitted. So the difference here is that if you're using an LED, you already have a broad spectrum. So you don't have the same problem as with the mercury spikes. And you can combine different LEDs like blue and red and then use some fluorescent materials to get the middle region. Yeah. So this is what I actually wanted to discuss. What color do you see in, let's say, over here? Someone orange, really interesting. Okay, what color do you see here? Red. But did you expect it to be as orangish as this? Right. And did you expect the light from the bluish illumination side to be as purple as that? So this is just some processing that our brain does. This is called color stability. So it is the ability of our visual system to keep the colors that we perceive relatively constant, irrespective of the illumination that has hit the object. And so we have seen over there that it depends on the light that's hitting the object, and the other factors that affect it is also the number and variety of objects in your vision, as well as the spatial arrangement of objects. But let's play a little more. What color is this water? Or, well, anywhere here. Greenish? Bluish, okay. Bluish, greenish, fine. And the snow over there, on the mountains. White and slightly pink here. So, okay, here. It's not actually greenish or bluish. This is actually a little bit much more gray than you might have expected. And here it's a pink, as you said. But I can take this one step further. What color do you see? The strawberries. Red. Brownish. Interesting. How many of you say red then? And brown for some reason. Okay. And what about blue? I heard blue as well. Blue. Okay, fine. I don't know why that's happening, but it is actually, so it's sort of a bluish gray. And turns out this depends on the projector, because I saw it on my phone and it's a reddish gray on my phone. So depends on the surface you're using to display all the sites. I'm talking about this color, not the strawberries. I mean, I saw this square on my phone and it looks reddish gray on my phone for some reason. So your brain here has recognized, at least those of you who saw red, it has seen that it has recognized the strawberries and filled in a red color to it. And this is, so we can say that the color that you perceive also depends on a cognitive bias. And now we can sort of try to discuss what your brain, the kind of processing that your brain is doing. So what is it trying to do? Let's say you were a monkey looking for an apple. In warm illumination, the apple would look like something, and in blue illumination, the apple would look like something. Both cases, you need to be able to make out that it's red in color, and that's what your brain tries to do. It wants to try to keep the apple red in different illuminations. The info that it has is the excitation of each cone. One second. I'll just. This I can use. And the excitation of the cones depends on the light that's reaching your eye. So we saw that the different light sources have different spectral distributions. So I'll denote that by I of lambda, and different objects will reflect different amounts of light at different wavelengths. So I'll denote that by R of lambda, and P is just the point in your scene, that's it. But the different cones also have different sensitivities to each wavelength. So I will also multiply by the sensitivity of the cone to the wavelength itself. And finally, that was, so if you just do this for one wavelength, then you'll get the excitation caused due to that wavelength, or a little bit at that range of wavelengths. And if you integrate over all the wavelengths, then you'll get the total excitation of the cones. And this is the info that your brain has. And from this info, it needs to be able to judge the color of an object without relying on the illumination. So, any thoughts on how it can do that? Okay, fine. So, it can try to compare the, how much. Okay, wait, now does this look red or does this look orange without the blue illumination aside? I'm just conducting an experiment now. Because from me here it looks red, fine. So, what your brain can try to do is compare how much this point in your vision is exciting each cone relative to other points in the vision. So here we'll just take one reference point. So you can see that integral there is weighted by R of lambda p. So if a point is reflecting different amounts of light at different wavelengths, the integral at the top and the integral at the bottom will be different. So this red surface, your brain can tell that this red square is exciting the red cone more than this surface. So it can tell that surface is redder than that, or any other surface is bluer or greener than some other surface, and combine the info from all the cones, and it can get an idea of the overall color of the object. But then it doesn't just use one reference point, it will take all the reference points across the image, within that circle there, to compare and use all the points to compare how much the point that you're looking at is exciting your cones relative to all the other points. But it doesn't even need to be a circle. So your brain can tell that the two images are having different illuminations. So it can just take the entire area where it thinks it has the same illumination and use all those points to come up with a color for each surface. And now what color do you see? This is a very famous meme, I guess. How many of you see black and blue? Nice. Okay. How many of you see yellow and gold? Huh? White. Sorry, my bad. White and gold. I see white and gold. Nah, wait. That's there. So there's also, see the projected, it's not, yeah, see. So the black portion itself looks kind of bluish over here. So there's something, wait, once again, Who sees yellow and gold? I mean, yellow and white. So it's like a 50-50 divide in this room. That's nice. I don't have to justify myself. If I was the only one who saw yellow and gold, I mean yellow and white, then it'll be weird. So let's go back to the factors that I had talked about. One of the factors is the number and variety of objects in vision. In this picture, there's not many things for your brain to compare the colors with and assign like proper colors to the dress. And you can see here the actual color that you're seeing for this yellow portion is some brownish color, and this is the white portion is actually somewhat blue. And this comes down to, like as I said, your brain doesn't have enough information about the scene to be able to judge the colors properly, and it has to assume an illumination now. It has to guess whether the dress is being illuminated by blue light or by warm light. And so for me, for the people who are seeing yellow and white, what's probably happening is these bright portions there, which are there because the photographer has taken a very long exposure picture, like way too long than it should be. It looks like afternoon sun, I guess, and the object itself is not in direct, like it's not being directly hit by the sun. So we assume it to be in the shade, and as I had discussed earlier, an object in shade in afternoon seems to have, I mean, it's under bluish illumination, and our brain assumes a bluish illumination here and tries to negate the bluish illumination. So then we think that since under blue light, this white strip over here, what I think is white, is reflecting all the blue light, we think that it is white. And the brown portion, well, under blue light it wouldn't reflect much light, so it should actually be like grayish, but yeah. So that's why we assume this to be what, white and yellow, yeah. And those of you who saw black and blue, yeah, black and blue, would have assumed a neutral or warm illumination, and probably your brain assumed this to be black and then shifted the colors accordingly. So in the sunlight case, our brains assume this to be white, and in the other warmer light case, our brains assume this to be black, and then shifted the colors accordingly to get to whatever colors we saw. And this is for everyone else to see a different perspective. So those of you who saw blue and black, tell me if this looks yellow and white to you. No, still looks, it's possible, yeah. I mean, depends on memory as well. If you saw the dress to be yellow and gold first, then it's kind of hard to convince yourself that this is again blue and black and the other way around. But you can still kind of try to fool yourself, but yeah.
So does this mean if we crop out the background that presumably everybody would see blue and black?
Maybe, yeah. But then you've also seen the dress already once before. So then you'll have to put in some different dress and like conduct the experiment again. Yes.
Can you go back to the last slide?
It changed color for you. So your brain just decided it's a different illumination while I was explaining. Wait, so did it change after you saw this? Okay, so you were able to convince yourself that it's some other illumination. Yeah. So the trichromatic model of color that Hariccharan discussed is only valid when the illumination remains constant. In reality, our eyes are always adapting to the surrounding illumination and all the other objects in the scene to decide on a color for each object. So now I call Hariccharan again to. Yes.
Yeah, so this slide tells everything that we have covered till now.
Oh,
So first we have
Fine,
light.
I thought it was all.
Light enters our eyes. Our eyes gives the LMS value. LMS value goes to the brain. It uses the operant process, allocates colors, and our brain does color stability, analyzes the entire image, and interprets the color. So this is entire perception. And now what we are going to do? Yeah. So everybody must know this formula. You would have done in JE. The section formula, the internal division formula. So let us consider a point A, and I am considering a point B. Using the section formula, I will be able to represent all points within A and B. Am I right? I can represent all points here. What should I do if I want to find this point? What modification should I do? So the formula is m into b plus b vector, n into a vector by m plus n. I have taken the points to be a vector. So yeah, we can take b, a as well. Yeah. What should I do? What modification should I do if I want this point? So that is the external division formula, right? We will take a minus here. M into, so if this is m and this is n, then m into b vector minus n into a vector by m minus n would give this point. So and here m, n are always positive. M and n are always positive. So what I am going to do, the same applies for colors as well. In the chromaticity diagram, if I have two colors C1 and C2, I can produce all the colors inside within C1 and C2 by changing the intensity of C1 and C2. And similarly, if I have a third color C3, I can produce all colors inside this triangle by changing the intensity of C1, C2 and C3. But if I want to produce a color outside the triangle, I can't produce that because I need to negate one of the colors, and there is nothing called negative intensity. So with this three base colors, I can only produce all colors inside this image. So now have a look at the chromaticity diagram. Tell me three colors in the chromaticity diagram that will cover the entire space, entire color space. Any three colors in the chromaticity diagram which will form a triangle that will include all possible colors. No. So RGB, so R is here, this region is R, green is here, blue is here. Even if I take this end and this end, I'll get a line like this till I have colors outside of it. So there are no, with three base colors, it is impossible to represent the chromaticity diagram. So all the screens are based with three base colors only. All screens have pixels. Every pixel has three light sources, one for green, one for blue, one for red. So no screens can represent the entire chromaticity diagram. No screen in the world can represent the entire chromaticity diagram. And you may ask, then how am I able to see a chromaticity diagram here? Yeah. Yes, it is the closer representation of the chromaticity diagram. This is not the chromaticity diagram. So what you are seeing here should actually come here. So let us assume this is the color system for us. Let us assume REC 2020 is the color system for the projector. So this color would be here and this color would be here. So the projector system is just expanding its chromaticity space, color space, to cover the entire chromaticity diagram. So it is impossible to see the entire chromaticity diagram on a screen. So these are the various screens that have been designed. The original screens were sRGBs. So this was it. They covered only a very small region of the chromaticity diagram. This is because of the problem of producing a proper light source. They used this for blue, this for green and this for green. Sorry, this for red and this for green. That is much far from the other point. So yeah, and the modern screens use the REC 2020 systems. to represent colors. So now let us look at some screen based color system, RGB and HSV. So these are something which you will use in image processing. So what is the RGB system? RGB is much simple. Every pixel has 3 light sources. Every light source has minimum intensity 0 to the maximum intensity 255. Why 255? Yeah, so 0 to 255 has 216 values, which is 16 into 16. So one value I will use a hexadecimal number. This is also a hexadecimal number. Without, I can represent the entire RGB color code with just 6 values. For example, I can use 1F, 11, 9, 1. So this represents 1 into F. F is nothing but 15. So this is 15, this is 1 into 1, 1, this is 9 into 1. Yeah, so this is how you represent. This is actually 9 into 16 power 1 plus 1 into 16 power 0. So with this you can represent all possible colors. So this is the RGB cube. If you see, this is red, yeah, this is blue, and that is green. What is this color? This is yellow, and anybody knows these 2 color names? Yeah, so this is magenta and this is cyan. So yellow is anti-blue and magenta is known as anti-green and cyan is known as anti-red. So we have white at this vertex of the cube and behind we have black. Now apart from the RGB system, we have the HSV system. It is actually easier to produce colors with the HSV system than the RGB system. So this is what you use in whatever be the software you use, Paint, Canva, and all the system to select colors. You actually use the HSV system. So in the HSV system, H is hue, S is saturation, V is value. Value is nothing but the maximum intensity of one of the 3 light sources. It corresponds to intensity. S is nothing but saturation. So what we define is that we can go to the chromaticity diagram. In the chromaticity diagram, I define the saturation of white to be 0 and the saturation of the spectral colors to be maximum. So as I move from white to the spectral colors, I would go from 0 saturation to maximum saturation. And hue, to define hue, what I am taking white as a reference point. I am defining hue of red to be 0 degrees. And I am just going to rotate it 360 degrees. So at 360 degrees, again the hue is red. Hue equal to 360 degree corresponds to red. Hue equal to 120 degrees corresponds to green. Hue equal to 240 degrees corresponds to blue. So with this I represent the HSV system and this is the HSV code. So as I move from this tip to up, I am increasing the value, and from here to here I am increasing the saturation, and this is hue. With this HSV cone I can represent all colors that my screen can give. So now let us see how the RGB system and HSV system are there with a graph. So here if you see, you have a RGB cube. So you will be able to see all the 8 vertices. So yeah, so here you are seeing red, this is magenta, this is cyan, this is blue, this is yellow, this is white, this is black. If I rotate it, you have green. Now where is the point of maximum saturation is white. Sorry, minimum saturation is white. And when you are moving from red to white, what is the value you change? Red to white, sorry. When you are moving from red to white or blue to white or green to white, what is the value you change? Hue or saturation or value? Saturation, yeah. So as you move from red to white, we are actually changing the saturation. So in these 3 faces of the cube that are adjacent to white, we have a constant value, the maximum value. The value is maximum and the saturation, hue are changing. Now I am going to the other three faces of the cube. So this is black. Yeah, so what is the value that changes? So when I am going from red to black, what is the value that changes? What component is changing? Hue or saturation or value? Value. Yeah, value is the thing, a component that changes here. So it is hard to tell value. Yeah. So for these three phases, the saturation is maximum. Okay. Yeah. Now let us see a new thing. This might be interesting. The biological aspects of colors, how other animals see colors. So everybody might have seen this. So this is the image which we see. This is the image a dogs see. Why are dogs' image much different from our vision? Sorry. Yeah, they are red-green color blind. They have only 2 types of cones. They don't have 3 types of cones. So most of the mammals have only 2 types of cones. These dogs. We have 3 types of cones. Why did we develop 3 types of cones? Is because as you mentioned in the earlier part of the class. So when we were primates, we wanted to distinguish between ripened fruits, unripened fruits, fresh leaves and dry leaves. That is why we developed the 2 different types of cones, so that we can differentiate between red, yellow and green. Other animals can't do that. They see red and green the same. Red and green appears the same for them. So that is why tigers are orangish in color. Orangish in color, though they are in a green jungle. So it should be easier for deers to spot them, right? But deers can't see them because they are red-green color blind. So tigers look the same as the background, green in color. So they can hide in the background. So yeah, so for dogs specifically, the maximum value occurs at 420 nanometers and 565 nanometers. So now let us look at the graph of it. So this is the graph, and if you see here, this graph corresponds to the value for human beings and this corresponds to that of dog. What is the difference which you see? This is the one for dogs and this is the one for human beings. As you can see, for a dog it varies in only 2 dimensions, but for humans it varies in 3 dimensions. It is because we have 3 basic types of cones and dogs have 2 basic type of cones. So our colors are expressed in 3-dimensional space, but for a dogs it is expressed in 2-dimensional space. This is how it looks like. So now if an animal has higher number of cones, then its colors are distributed in a higher dimensional space. For example, honeybees, their colors they have 4 basic colors. They are tetrachromatic. Their color system is expressed in 4-dimensional space, and we can't see 4 dimensions. And birds, some aquatic animals, even their colors are distributed in 4-dimensional space. They have different varieties of colors. So honeybees can see ultraviolet, blue, blue-green and yellow. They can't see red. Red appears black for them. So as honeybees slowly gained the ability to see ultraviolet, some flowers have evolved in a counteracting way to have pigments that are only seen in the ultraviolet colors but not in visible light. For example, if you see evening primrose, this is how it looks under visible light, and under ultraviolet light you will be able to see some special patterns. These are specifically for the bees to spot them. And now let us come to another interesting topic. Yeah, so this actually says how we see different colors. Okay. So yeah, what do you see in this image? What is this organism? Octopus. So yes, so this is an animated GIF of octopus. So now we are going to see how octopus is actively changing its colors. What is the speciality of it? So octopus has two main types of cells or tissues on its surface that helps us to change colors. One is chromatophores, the other is iridophores. What are chromatophores? Chromatophores are much easier to explain. They are just sacs of pigments which varies from yellow, red, brown, black. So whenever they want to change their color, they will just increase the size of this chromatophore and hence changing their color. These chromatophores are present on the outer surface of octopus. And now when we go to iridophores are specifically for the lower wavelengths of colors like blue and green. So what they do is that they have these layers of guanine. All these are made up of the amino acid guanine. These are in alternating these have alternating refractive indexes. So lesser refractive, rarer medium, denser medium, rarer medium, denser medium, rarer medium, denser medium, so on. So whenever the first light hits a denser medium, it gets reflected with a phase shift of 180 degrees. You guys may know, whenever there is a reflection, there is a phase shift of 180 degrees. Light enters and now it gets reflected from the rarer medium. There is no phase shift. So again it goes here. But the problem is that, and now what is the thing is that this extra distance covered by this light is exactly equal to lambda by 2. When it is exactly equal to lambda by 2, this light and this light will constructively interfere. If this distance is not equal to lambda by 2, these two lights would not constructively interfere. And I have several layers. Now all these lights will constructively interfere only for a given lambda. So only one particular lambda will get reflected, all other lights will not get reflected. So octopus, this is what we call iridophores, and this phenomena is called iridescence. So octopus, by stretching or compressing the iridophores, it can change the light they reflect. So what is so special about octopus is that they don't just use colors to hide with the background, to match the background. They also use colors to mimic other animals. And another special thing about octopus is that they don't see colors. They can see only black and white images. They don't have cones. So then how do they distinguish colors? How can they mimic other organism or match with the background? So octopus eyes has a lens which has a very high chromatic aberration. So when light enters the lens and hits the retina, only one particular wavelength will get focused exactly. Other wavelengths will not get focused on the retina. There will be a blurred image. Only one particular wavelength will form a clear image. So with the clear images and blur images, the octopus is able to distinguish what is the color of the objects that are present around it. So if you see here, these are the various mimics that are done by the octopus. It can mimic like a flounder. Flounder is a predatory organism. When octopus makes this shape, a flounder would think that this is another flounder and it will not eat it. So this is an octopus mimicking like a sea snake. So when it mimics a sea snake, the other fishes won't attack the octopus. So these are the various mimics made by the octopus, like a lionfish, sea snake, jellyfish, flatfish, sea anemone, crab and mantis shrimp. So many mimics. Yeah, and this is a video. Oh, sorry. I can't hear. Okay, fine. This is the octopus. It is mimicking a coral rock. Yeah. And yeah, next animal is the, what is this animal? Dinosaur. Wow. So this is a chameleon. So chameleon's color system is much similar to that of octopus. Even they have chromatophores and iridophores, but their chromatophores are in the deeper layers of skin, unlike an octopus. And chameleons can use both hormones and nervous system to control their colors. Apart from that, chameleons not just use their colors to camouflage, hide with the background, they use it to challenge rivals. So if a chameleon is in a tree, another chameleon is visiting the tree, The chameleon which want to exert dominance will express itself in bright colors, and the chameleon which does not want to exert dominance will express itself in dull colors, and it use such colors for mating as well. And then we are coming to another beautiful animal.
So this morpho butterfly, you can see that it displays a very bright, a very brilliant and vivid blue color. The color blue is sort of rare in nature. Can someone tell me the color of a blueberry? Blueberry, what's the color of a blueberry? Who said blue? It's purple. Yeah, but still, you have there are still some blue birds that biologists have creatively named bluebirds, and there's some blue flowers which thankfully are not named blue flowers. And the special thing about the morpho butterfly is if you grind up its wings, then you don't see a blue color anymore. You'll see brown instead. So the color is not due to a pigment in the morpho butterfly. It is due to the structure of its wings. So you zoom in, and then there's like a bunch of scales like this. You zoom in even further, then each scale has ridges running along this direction, and each ridge itself has transparent extensions made of chitin, which have a different refractive index compared to air. So because of this, you have the multi-layer interference that Hariccharan talked about earlier, as well as diffraction and total internal reflection within the lamellae itself. The combination of these three effects together give you this bright blue color. And the interesting thing is that since it's dependent on interference, if you put a droplet of ethanol on the wing, then the color that you see changes, and as the ethanol evaporates, the color returns back to blue. And so as you change the direction of at which you look at the wing, the color remains roughly constant, which is something that you wouldn't expect from diffraction, since the colors in a normal diffraction grating, you'll see them to be dispersed, like similar to the prism thing itself. So you shouldn't see the same color. But over here you have a little bit of randomness in the ridges. So different ridges, over here they've plotted only up to 400 to so this is degrees intensity of light, and what is that? That is, each different line is different wavelengths, and they've plotted it for 400 to 500 nanometers, which is basically just blue light. So different ridges are giving me a maximum intensity of blue light at different angles. So here it's at 60 degrees. Here it's sort of evenly distributed between -30, 0 and 30, and here again it's somewhat distributed, and so here it's the same like that. So the combined effect of all these different ridges, and these are just 4 ridges, there are like 4 ridges that they've tested. So the randomness in the ridges itself allows for this broad angles at which you can see blue light. And with that yes.
So wait, don't change. So at last what we want to tell is that vision is a very important part of our life. So, and colors make an important part of vision. So colors helps us to see the world. So colors are a guide to the world. They are a guide to the entire universe. They also act as a guide to the galaxy. Yes. So with that, this is me, Hariccharan and Srikiran, concluding our second Guide to Galaxy session of this tenure.
This is our WhatsApp group. anyone who hasn't joined, please join. We'll be giving out information about the other sessions that we'll be having, Guide to Galaxies like this one, as well as sessions where professors will come and talk. And one of those, so we call the sessions where professors come and give a talk, Quarks to Quasars. One of these is going to be on 23rd, right? 23rd. And it's going to be about gravitational wave astronomy. Yes, by Professor Suresh by Professor Suresh. That's it. Last name I forgot. But please do consider attending this Quarks to Quasars session as well. And that's it.
Yeah.
Thank you for attending. I didn't expect these many people to come on a Sunday.
And please do scan these QR codes. One is for our WhatsApp group, the other is for the references which we took for the session. Yeah. Thank you. Yeah.